But then I just, I know. Yeah, someone already has it. Well, yeah.
Just waiting for Dawn. I think she's just.
Yep.
Well, if we can do this type of processing also on the detection side, that would be a heavy lift. And I just feel like overall results, it's going to be hard to get in, especially compared to other archives. The reason I want to keep going is because right here, so some more experimentation and maybe a little bit of mechanism would be very strong.
It's funny, I posted a picture of like programming. I'm just getting there. I also got 20 questions to ask my potential roommate. You can just Google it and find it. Yeah, right. That's pretty interesting. It's like, yeah, you just cover all the bases you need to cover, and it's pretty straightforward.
Well, why don't we get started?
Sure.
Well, it's
Yeah.
not funny, I have a friend.
I have a couple really quick announcements before we get started. Next week is the poster session, and shortly after that, the final project report is due. So there are posts on Piazza about this. At the end of class today, HCAN, the undergrad computer science association, is coming in to do a the last 10 minutes of class to do a quick survey about the class and get feedback. So this is relevant for people who are taking the class. I think that's all the announcements. Okay, so we're very fortunate to have Ryan Adams speaking today. So Ryan has was at Harvard and has spent time at Twitter and Google, and is currently at Princeton. He's done a lot of really fascinating work in deep learning, probabilistic modeling, and combining these together. And I was actually very fortunate to get to work with Ryan when I was an undergrad. Well, thanks a lot.
Well, thanks for having me. It's really fun to be here and get to sort of see old friends and colleagues at Berkeley. Today, what I'm going to tell you about is thinking about how to combine probabilistic graphical models and the associated structures that you get from them with deep learning, which I'm kind of calling here massively parameterized models. And I'm going to kind of take a kind of a semi-parametric view on the world and try to talk about how these, even though they kind of feel different, and one is like the way people were doing machine learning kind of maybe in the 10 years ago, and the other is how people like to do machine learning now, but I think they're kind of like much more complementary than we often sort of give them credit for. And I kind of want to tell you about how we think about that and how we try to do science with by combining these kinds of things. And so to that end, I want to show you this guy. So for the last several years, probably since like 2013 or so, maybe 2012, I've been collaborating with Bob Data, who is at the Department of Neurobiology at Harvard Medical School. And he is trying to understand mouse behavior, and in particular, naturalistic mouse behavior as a model, of course, for the way humans act. And basically, the kind of science that Bob wants to do and that we're trying to do in this collaboration is to understand that if we give this guy a drug, or we modify his genes, or stimulate its brain in some way, or expose it to fox pheromone, or whatever it is. We want to understand how its behavior changes. Okay? And you can see immediately how this is relevant for thinking about drug design and the science of understanding human behavior. This is a very hard problem, though, and because mice are complicated little things. And so the way people have often gone about trying to do this, well, I would say there's kind of two broad approaches. One of them is to try to take a very, very complicated set of mouse behavior and turn that into a very simple scalar that can summarize everything about a mouse. So this is an example of how to produce such a scalar. So this is called an elevated plus maze. So there's there's like a plus-shaped sort of platform. Some of it has kind of shields around the side, kind of walls. And basically people have decided that mice who are anxious like to spend less time out on the exposed portion of the plus. All right? And so if you want to develop an anti-anxiety drug for humans and you want to understand its effect on the mouse model, and you'd like to be able to have nice sort of statistical results for that, then maybe you give the mouse these drugs and you then look at what fraction of the time the mouse is spending out here versus in here, and we call that our result. So that's one number that is summarizing kind of all of this mouse's behavior. But of course, mice are complicated kinds of things, and we'd like to be able to ask more complicated kinds of questions. One other kind of thing that people have tried to do to sort of get at this is instead to ask grad students to label frames of video, and to try to, so we take a bunch of video of a mouse, and then grad students spend their days deciding what the mouse is doing in every one of these frames, and then we get kind of a more sort of a richer sequence of what the mouse is up to. But this is problematic for other reasons. One is that the inter-observer error rate of such an analysis is something like 60%. That is to say that if we run such an experiment here at Berkeley, and then you do the same kind of experiment, ideally under the same kind of circumstances, but with different grad students and different mice at Harvard, then they're in general not going to agree on what the mouse is doing. But even if they did agree, it's problematic because it's necessarily anthropocentric, right? It assumes that the mouse is doing things that humans can understand and put language to, and it assumes that those things are happening on a time scale, like a human time scale. But there's no reason that the mouse needs to be doing anything that humans can easily understand and describe, or that it be doing it on time scales that are relevant to people. So the question is, can we use machine learning and computer vision and deep learning and probabilistic models and kind of all of the tools that we have available to us in order to do a better job and do unsupervised learning of mouse behavior that we can then use to inform questions about the effects of drugs or the effects of a wolf pheromone or whatever it is. And so these days we have things like depth cameras. So this is basically a Kinect that's pointing down at a freely behaving mouse. That's appealing also because mice behave differently in the light than they do in the dark, and they like the dark. And so something like a depth camera helps you capture that behavior. So we have better instrumentation. We have faster computers and GPUs and TPUs and all kinds of things. And of course, we know how to do modeling that we haven't been able to do in a long time. And we'd like to figure out how to blend all these things together in order to be able to sort of get new scientific insights. So the way we think about this problem is we think about it as trying to kind of learn a language from scratch. So you can think about the mouse is exhibiting a language of behavior. We think of individual behaviors as kind of like syllables. That is that there's little discrete bouts where the mouse is doing a thing, and then across many different mice and different populations and different situations, we see the same kinds of things over and over again. And so trying to go from frames of video to this discrete representation, you can kind of think of that as saying, I have a lot of recordings of people speaking, so raw audio waveforms, and I'd like to induce syntax, like language syntax from that. And that's essentially what we're trying to do here with video. We want to take a lot of video, millions of frames, and try to turn that into a set of shared discrete states across many populations, and also dynamics over those states. All right? That then we can see, and the idea then being that we can see how those are modulated by different kinds of things we might do to the mice. So if we change its genes, change its brain, then does that cause it to do sort of more of one thing, less of another, or maybe modulate interesting sort of second-order interactions between these guys? So if we were to take this kind of problem, and particularly if you were to sort of tackle this using what you might think of as like the dominant paradigm of machine learning of 10 or 15 years ago, and build a build a probabilistic graphical model, then a natural way to maybe think about this would be something like a switching linear dynamical system. So here the idea would be that we would have some nice, interpretable, hopefully latent discrete states with sort of Markov transitions over them. And then those discrete states would each own a local linear dynamical system. So you would have discrete latent state and continuous latent state. And depending on what discrete state you're in, you're applying different linear dynamical, sort of linear dynamics to that continuous state. And this is appealing because of this idea that we think we have stereotype behaviors that are sort of extending for 200 milliseconds or something, but that ultimately sort of mouse physics is continuous, right? That there are joint angles and position and velocities and everything. And that those things are somehow kind of smooth and relatively simple. So we could write down a probabilistic graphical model with our sort of 2005 modeling hat on, and we'd have these nice discrete states. Then those would be modulating continuous states. We'd have some set of global parameters governing everything, and then hanging off of that, we would have these frames of video. Okay? So this is like an appealing conceptual way to tackle the problem. But in a really fundamental way, this doesn't work. And the reason it doesn't work is because asking something like a sort of Gaussian emissions like you would get from a switching linear dynamical system, trying to connect those to very high dimensional data, in general fails. If who's ever tried to take, like a Gaussian mixture model and apply it to high dimensional data like images? A few people, right? And it sticks, right? Like it doesn't work because it's just because the density is such a bad model for these high dimensional data, and sort of gets drug around by the sort of many different ways we could explain it. So somehow we'd like to be able to have models like this that have likelihoods that are flexible and rich enough to be able to connect to something like mouse video. So that's the fundamental kind of agenda here, informed by these scientific questions that I think come up in a lot of different domains, which is how can we take our nice structured probabilistic models that have been successful in many, many other domains, and how do we connect them to something really high dimensional like video? And then how do we do inference in such a model when for this to be interesting science, we're going to need to be looking at say tens of millions of frames of mouse data. So that's the kind of the name of the game here. And I feel like an important thing to kind of say out loud as a part of this is that it's, I think, useful to think about why deep learning has kind of been successful. And I think a lot of it basically boils down to the fact that deep learning often has very good priors for these high dimensional data. In particular, I think if you kind of ask the question, like, what are the situations in which deep learning really works, it's situations where you can express some kind of invariance, in particular convolutional invariance, and identify some parameter sharing that kind of makes sense for your data. So whether it's images or audio or text, we often have this notion of some kind of translation invariance that leads to success. And actually, it's a little bit difficult to come up with really it is both sort of difficult to identify problems where deep learning has been really successful that doesn't have some notion of invariance like that. And it is also interesting to note that even though I kind of call this a prior, it's quite hard to come up with like a probabilistic graphical model that has this kind of prior in it. So we'd really like to be able to take advantage of this kind of parameter sharing and this kind of structure in something that feels like a probabilistic graphical model. So there's kind of a spectrum then of different ways we might think about modeling our mice. So the classic sort of statistical view on this is we're going to try to construct the problem to be as simple as possible, right? So it has simple data, and so we have strong statistical analyses we can do on this simple data, and turn it into a linear regression or some straightforward hypothesis test. But necessarily, that's going to lead to relatively simple hypotheses that may not allow us to develop the drugs we want to develop or understand the relationship between genes and behavior that we want to be able to understand. Another extreme that is sort of maybe the current sort of zeitgeist would be to say, well, let's just throw like your favorite recurrent, residual, convolutional, yada yada, big neural network at it. And that will get very good at predicting the next frame of video, but it will not necessarily let you sort of go in and be able to understand what's going on in terms of sort of underlying hypotheses. It doesn't let you necessarily talk about, say, the upregulation of a particular discrete state that you might decide you care about. What it will do is allow you to generate a bunch of new data, right? But data is relatively easy to get because you just need a box, a mouse, and an undergrad. And so so we'd like to be able to somehow find a balance between these where we can look at complex data, but we can build a kind of a structured model and be able to couple these things together so we get richness and interpretability at the same time. And I like to think of this as a kind of semi-parametric modeling because I really think of deep neural networks as being non-parametric models. That sounds like kind of a funny thing to say, but non-parametric to a statistician really means massively parametric, right? It really means, it is not that you don't have parameters, it's that you have a tremendous number of parameters. And I really think modern deep learning fits that description. And in fact, there's been, of course, deep connections drawn between things like Gaussian processes, which are formal non-parametric models, and neural networks. So let's just sort of talk about that in the context then of a little bit of toy data here. So let's imagine that this simple pinwheel data, that maybe each of these little dots is like, imagine it's like a frame of video. Okay, and imagine we want to come up with, we want to do unsupervised learning of these data, and we'd like to, maybe come up with something that both models this density and has some interesting interpretable structure. So if you put on your sort of like 2005 probabilistic graphical models hat, and you take a Dirichlet process mixture model, and you apply it to these data with a bunch of sort of Gaussian observations, you will be able to model the data quite well. You will, in the sense that you will be able to model the density. Right? But because your Gaussian distributions for each of these little components is kind of quite sort of impoverished, then you wind up losing all interesting interpretability and over-segmenting the data, right? If we were to go in and look at the identities of these components, we would find this pretty unsatisfying. Like our visual system sees some structure here, and this guy is sort of massively over-segmenting it and destroying that structure. On the other hand, if you used a variational autoencoder or whatever your favorite sort of neural density estimator is, you could also model the data well, right? You can, in the sense that you could model the density well. It's just now you're headed the other direction. Now you're under-segmenting this, and what's happening is we're able to use the highly nonlinear function represented by the neural network to take something like a latent Gaussian and kind of like warp it and shape it until it's able to capture this density. Still, we're not very happy because we haven't discovered some of the kind of interpretable discrete structure that we think might exist. So the sweet spot we're hoping to find is something like this, right? Where we're able to use flexible, massively parametric models to capture the components, but we still have discrete structure that makes itself available to us in the inference. So this is kind of living the dream, where we can model these components flexibly, but still find parsimonious discrete structure. So the name of the game is to take the models that we've had before and use neural networks to make them a lot better. And neural networks help us in two interesting and different ways. So one thing they let us do is go from things like simple latent discrete variables at each of these time steps and build really complicated and richly parameterized likelihoods. That is on the generative side, where we're going from latent structure to visible structure. We can make that big and complicated in interesting ways. And then they also let us do inference, because when we make things big and complicated on the generative side, it always makes inference hard. And so here I mean reasoning about the posterior distribution over both global parameters and all of the local structure that's going on in every little sequence of sort of mouse behavior. And so what we can do there is use neural networks to help us with inference. That is, we can go from, say, a picture of a mouse or sequence of pictures of a mouse to an approximate posterior distribution using what we often now call amortized inference, which just means that rather than doing sort of bespoke inference for every one of our examples, like we might do in the sort of variational setup, we instead have a neural network that's going to produce that output. And so the point is that I view these as being complementary kinds of technologies, that we'd like to be able to use probabilistic graphical models to tackle really big problems in high dimensions, and neural networks are exactly kind of the right tool for that job. And I think if you're a methodological person, you need to always stay committed to trying to use the right tool for the job. And neural networks aren't the right tool for every job. Probabilistic graphical models aren't the right tool for every job, but together they can kind of be bigger than they are individually. So let's talk about the likelihood aspect of things first. So we have our switching linear dynamical system here. And what we want to be able to do is take something that looks like, take this kind of latent continuous state and turn that into some high dimensional output. And a very straightforward way to do that is to pump that latent state into a neural network, and then have the neural network output means and covariances, possibly very simple structured covariances for the observations. So that is, think of this like we're going to take the latent state and it's going to produce an image by producing a mean for every pixel and a variance for every pixel. And then that's something we can easily sample from and evaluate its density on C data and all the nice things we'd like to do with a likelihood. All right, so this is so it's the likelihood side of this story is actually kind of quite straightforward. It's just saying I have a complicated, I want to use a complicated function to parameterize a Gaussian. We could do this with other kinds of observation functions, but here, but for like image data, where we're going to treat it sort of as a big high-dimensional continuous vector, this is a natural thing to do. So we can boil this off, this kind of simplified structure, into a couple of different pieces then. So we start with some we start with some probabilistic graphical model. From our point of view, we can kind of say, okay, well, the time aspect of this is kind of not fundamental, so we don't really need to worry. So we'll kind of like cartoonify this a little bit by removing the time element, and then we'll cartoonify it further by removing by also kind of pretending like there's only one kind of latent variable structure. And suddenly now we have an object that is a cartoon for many different kinds of probabilistic graphical models coupled to neural networks. So there's some stuff sitting up top. So we're going to have some kind of global variables, right? And then we're going to have local variables. So this is using the language of, like, you read the stochastic variational inference paper. This is using sort of Dave Bly's language for global variables being kind of things that are shared across all mice and all sort of sequences of videos of those mice. Local variables then might be things that are idiosyncratic to individual mice or individual frames or individual video sequences. Okay? So we're going to imagine that the latent structure in something like a switching linear dynamical system is nice and simple, and maybe is exponential family and with conjugate priors and the kind of the really nice place we like to live when we're doing probabilistic modeling. And then what we're going to do is hang off of that a massively parametric neural network that is going to actually be our observation model. Okay, so there's going to be two different kinds of things going on, and what I hope to convince you of is that these aren't as different as they at first look. One of them is very nice conjugate structure. The other is sort of massively parameterized function approximators. What's nice about that cartoon is that you can immediately see how we could hang high-dimensional data off of lots of different things. And again, sort of, if we sort of think back to sort of machine learning of sort of like 10 or 15 years ago, people came up with all kinds of interesting different ways to write down probabilistic graphical models to capture, data evolving over time, topic models, mixture models, all kinds of different ideas, and that we could, in principle, take the sort of observation distributions of these and use neural networks for them. And what I'm going to convince you of, hopefully, is that in each of these cases, people thought hard about how to do clever inference and use dynamic programming and things to sort of handle the nice exponential family structure. And we don't necessarily have to give that away when we couple them to big neural networks, it turns out. So let's talk about inference, because that's kind of where the hard part is. It's always easy to like write down a generative model to get some data. It's another thing altogether to ask the question of like what are the latent structures that would have generated those data. So the high level picture here is we're going to do mean field variational inference. So that just means I'm going to come up with a factored approximation to the posterior distribution. And here the factoring may not be all the way down to the sort of level of each individual variable, but I'm going to choose some sort of coherent product over the latent state. What's really nice about the variational formulation is that unlike Markov chain Monte Carlo or things like that, where I would have to turn my Bayesian inference problem into a very difficult integration, variational inference allows us to think of this as an optimization. And optimization, you can pull sort of any tricks you want to do better optimization. Whereas something like MCMC, you have to you sort of have to satisfy a lot of different conditions. So we like optimization better. We're going to get to take advantage of stochastic optimization. So here we're going to do kind of Robinson-Monroe mini batching and get stochastic gradients to do that optimization. And what we're going to see is that conditional conjugacy of the form that we get in these nice exponential family models is going to allow us to actually do natural gradient descent in the style of stochastic variational inference. And so that's going to be very nice. We're going to be able to take advantage of the Riemannian metric that arises from the underlying probability model. So you should think of natural gradient, maybe you've already studied this in this course, but you can think of natural gradient as a way to reason about the geometry of parameters via the way that it changes the actual distribution on the data rather than the Euclidean metric of the parameters themselves, which may be totally arbitrary. Okay? So that is to say, we want to take steps that really matter for the model versus steps that matter for the parameters. But for the pieces that we can't do that are going to be non-conjugate arising from the neural network, then we're going to use we're going to do amortized inference for those. So that is, we're going to learn another neural network that hands us the parameters. So a quick refresher on variational inference. I know this is a deep learning course, but so I thought I'd give you kind of a quick slide on sort of the variational inference setup. So we have some model that has maybe global observations y, observations y, local parameters x, global variables theta. Our sort of generative model couples these together into a joint distribution. We're going to approximate these with we're going to approximate the two things we don't get to see with factors. These factors are going to be exponential family distributions that have their own natural parameters. And the broad idea here is that we can lower bound the log marginal likelihood and then basically turn this problem into one of maximizing this lower bound in terms of these natural parameters, and that turns out to also be equivalent to minimizing the distance between our approximation and the true posterior distribution. So we wind up with a new objective that we're now just trying to minimize in order to do inference. That is we're trying to sort of maximize this function L, this evidence lower bound, or elbow. So stochastic variational inference is this idea in something like a linear dynamical system where we have two kinds of things we care about. We have these x's that are the local, and we have the thetas that are global. We have a factored distribution that breaks them down into, in this case, two pieces. One is a kind of a structured variational term over the local variables across time, and the other is global. Then the idea is we can sort of write down that lower bound and the log marginal likelihood. And what's really cool in such models is that it turns out that we can, at any given moment, we can find we can solve an optimization problem to find the optimal local variables given the data and our current global parameters. And so we can rewrite this overall objective as an objective just defined in terms of the global parameters. All right. The reason that's interesting is that it allows us actually to do natural gradient optimization very, very simply, because now the gradients that we need to take turn out to just be the expected sufficient statistics. So this is a kind of a very nice result. And it turns out that sort of, in a sense, natural gradient in a model like this is actually even easier than sort of flat gradient descent. And then if we sort of draw boxes around these guys and imagine that we have a whole bunch of data, then we can do the same thing, but now we're going to get to take like mini batches across all of our data to fit this with stochastic gradient descent. So the cartoon of stochastic variational inference then is basically we have some evidence potentials, the sort of stuff arising from our data induces some kind of local potentials on the different latent variables we're trying to estimate. We can use some nice fast message passing algorithm in order to compute the sufficient statistics and the properties of the global variables, and then those sufficient statistics tell us exactly kind of like what to do next to take our gradient step. So it's a very nice and simple algorithm, and really efficient when you have that structure available to you. The problem is we want to model high-dimensional data. We're going to have these high-dimensional likelihoods. Probably these sort of nice algorithms aren't going to work for us. And specifically, it's because since we have this big nonlinear likelihood, we're going to wind up with some posterior distribution, right, that is complicated and that is not simple for, sort of is not going to lend itself to kind of really simple local evidence potentials. And so the idea is that we can, instead of trying to perform that optimal local inference, we can ask a neural network to look at the data and try to just induce a good local potential that's going to be good for variational inference. And so we can parameterize that with some, say, set of parameters phi, gives us a potential. And literally what it does is like, think of it like a ComNet that looks at the frame of video and tries to guess kind of approximately like what would variational inference have wanted for the Gaussian associated with this frame. So this guy's a neural network. I mean, it doesn't have to be, but that's a very nice way to write it down. And we call this kind of structure a variational autoencoder. So this is Kingma and Welling. I think you read this paper for the background. So an autoencoder, of course, classically is this idea that I'm going to write down a big neural network that is going to implement the identity function, but it's going to have be learning the identity function with some bottleneck. And then the hope is that the bottleneck is like really squeezing out all of the interesting statistical structure when you learn it, such that you wind up with some kind of compact code. The idea here is that instead of inducing a code with that sort of first half, you're instead inducing a posterior distribution. All right? And just like whereas the decoder before, we would just think of that as a function that goes from code back to observation space as the other half of the identity. And the variational autoencoder, that's our generative model. That's the likelihood. Okay, so that's the kind of the way we're thinking about things. We have this this recognition network that is inducing a variational posterior distribution, and then we have this likelihood that is the decoder. And one of the things that's nice about this setup is that now we can still train this whole thing by maximizing that variational lower bound. What we're doing here is expanding the set of things that we can induce that variational posterior distribution over. So you can almost think of it as instead of just cooking up a Gaussian distribution for the latent state, think of it like it induces like a conditional random field. Okay. Something that people used to think a lot about. But it's like a Markov random field, but it conditions on some observations. So we can break down then things into three different kind of worldviews on how to do modeling. Natural gradient stochastic variational inference is super nice in the case where we have conjugate structure. It's expensive in general, because if you don't have conjugate structure, then you're solving intermediate obnoxious optimization problems. But when you solve them, you do get the optimal local factor, and it can exploit all kinds of structure in order to be able to get that factor when it's available. And it has the nice property that no matter what kind of marginals or conditionals or whatever it is you want to ask, you can ask that question. Okay, so that is to say that if I want to ask marginal questions about particular frames or particular states of a mouse or mice altogether, then I can ask those questions coherently by interrogating that factor posterior distribution. Variational autoencoders, instead of taking advantage of the sort of mean field variational setup, are just amortizing inference completely. And so that's awesome, because that means that test time is going to be super fast, because you're just blasting forward through a neural network. And so it's going to be, in general, something very easy to do. It doesn't involve a local optimization. But because it doesn't involve a local optimization, it's suboptimal, right? It's not, in general, going to give you the optimal local factor for any given problem. And because it's really asking this neural network to do sort of everything. One downside of that is that it doesn't allow you to ask general questions about the data. So now you can only ask questions that your amortized inference was sort of set up and trained to allow you to ask. And unlike the SVI case, we don't get natural gradients. We're just going to have to live with sort of flat gradients. Structured variational autoencoders try to find the balance between these two extremes. Take advantage of conjugate structure, natural gradients, and the whole bit whenever it's available to you, and use amortized inference when it's not. And so you get that. So it's fast now when you're able to use amortized inference, and because you're only going to not use amortized inference whenever you have conjugate structure, then you're able to still do fast things because you get fast message passing algorithms for that remaining structure. And it allows you to ask sort of complicated inferential queries because sort of up to the resolution of your amortized inference. There's a question. Yep. Oh, just stretching? OK. All right. So you can think of the structured variational autoencoder as kind of like this. So as before, we're going to compute evidence potentials, but rather than those sort of popping out of our sort of out of the vanilla likelihood, these are going to be induced by the recognition network. What's nice is that still lets us do, because it still lets us do fast message passing algorithms. As I said, we're kind of inducing a CRF. So we still get to do our nice probabilistic graphical model type stuff. Then we can push it down to compute the statistics, and we get flat gradients for the stuff that we have that we're amortizing, and we get nice natural gradients for the exponential family conjugate structure stuff up at the top. So we can have use both so we can kind of combine in kind of one optimization flat gradients from amortized inference and natural gradients from conjugate structure. That sounds like it might be sort of gluing things together a bit more than that doesn't seem necessarily maybe like a huge insight to be able to stick those things together. But it turns out that Matt Johnson, who's kind of the guy who's done most of this actual work, has come up with a very nice view that I'm just going to sketch briefly for you. So it turns out that you can combine both sort of variational message passing ideas and kind of flat gradient optimization into a single view through proximal operators. So just to remind you, the idea of a proximal operator is that we're going to sort of replace our optimization with a kind of auxiliary optimization such that we don't take too big of steps as we're performing the optimization. A very common kind of thing is the sort of linearizing proximal gradient update. But the reason that's interesting for us here, and again, I'm just sort of going to hand wave and sketch this out, is that in these conditionally conjugate models so that's to say a lot of the algorithms we're already using can be viewed as proximal operators for optimization. And in these conditionally conjugate exponential family models, it turns out that the log energy function that arises from these has a multilinear form. So if you think about the vanilla exponential family, that's like where you have an inner product between your natural parameters and your sufficient statistics. Well, you could think of that as basically sort of being tensorized. So you have multiple different kinds of variables that are interacting still through now a multilinear transformation. The reason that's interesting is because when we want to compute the expected negative energy, then it has like a really nice and simple form. As it turns out, you can derive the sort of vanilla proximal operator for that, and when you take the limit of the alpha going to 0 in that proximal operator, you recover exactly what you would do in the standard sort of mean field conjugate updates. So this is all a bunch of jargon that sounds kind of weird. So here's what I want you to think. Expected sufficient statistics are the way that you make stochastic variational inference go. And you can get those by taking the gradient of the log partition function, right? So what that means is that you can use automatic differentiation as a unifying sort of API for building both probabilistic graphical models and for doing neural networks. Okay? So previously, I think we thought about probabilistic graphical models as being something that required its own kind of worldview that was separate from the way that we trained neural networks, right? So whether probabilistic programming or you're specifying some complicated graphical model, like it felt like a very different kind of thing to do than the optimization you would do for like with TensorFlow or PyTorch or whatever. But because you can sort of view this through the lens of this like gradient of the log partition function, then you can actually see these as just being one kind of API. And that's appealing from the point of view of then just sort of writing one piece of code and using your favorite automatic differentiation software to implement it. Joey?
It's assuming exponential family, or?
Yeah, so what's happening, right, is that there's some structure in this that is exponential family and some that's not. And so if we think about then the this sort of negative energy, that's going to have a multilinear term that we can handle easily, and a term that's going to be annoying from our neural network. And so the point is that like we can kind of like differentiate into this, and it'll split off into hard flat gradients here, and automatic differentiation gives us the sort of the right mean field updates here. And it doesn't, so it's like one interface, but it sort of doesn't change the underlying computation. So it's nice because I think, at least certainly until Matt sort of demonstrated this, I felt like these were like two different worlds that were always going to be different, and there was always going to be people who thought about inference and people who thought about neural networks. And this shows that like automatic differentiation brings everything together. So we can look at a couple of examples of fitting this kind of thing just to give you a little bit more intuition. So here's back to this toy pinwheel data. And the thing to sort of think about here is that what's happening is the neural network is trying to find a way to warp the space such that the dumb Gaussian mixture model works, basically, right? So this is a latent space, and it's just trying to find a situation in which the sort of the thing you'd always like to do can work in a compact way instead of having to tile all of these little guys. It's almost kind of like it kind of, to me, feels like what it's doing is using the neural network to compensate for model mismatch in the likelihood. We can also look at, here's some other toy data. So this is like basically like a little one-dimensional world in which a puck is bouncing back and forth. We can model this with a little linear dynamical system. It's not linear because it's bouncing, right? And so, but the neural network can compensate for that. And so what happens is it learns the sort of local model and then learns the sort of overall dynamics. So here at the red line, it's projecting, it's sort of guessing what's going to happen sort of after that. So because it's modeling it with this latent dynamical system, it's able to make quite sort of long-range predictions. Getting back to the mouse data, which is what the kind of motivation for all of this was. And when asked for the papers, I gave you this neuron paper that maybe some of you looked at. It was one of, I think, the optional readings. And the neuron paper doesn't do any of this, right? And so the scientific story here for us in the development of this maybe is worth saying, which is that we worked on this problem for a long time, this problem being the mouse problem, trying to come up with unsupervised learning that really did work under a lot of different circumstances and let us sort of solve the mouse problem the way we wanted. And it was only after writing that neuron paper with linear setups and kind of random projections that we realized the variational autoencoder kind of let us model the mice a lot better. And the way we think about it is to think about the sort of manifold of mouse behavior, right? And that what we want to do is find a manifold in the depth video such that there are relatively simple dynamics when they're constrained to that manifold. All right, so can you sort of warp the space in such a way that like a switching linear dynamical system is a good explanation for what the mouse is doing? So in this case, kind of like segmenting hypothetically between different behaviors in this lower dimensional setup. And so we can look at lots of different actual data, some of which is synthetic, some of which is not, and it's quite difficult to actually tell the difference between real data and synthetic data. But more interestingly, from the point of view of doing the science, we can take a bunch of real data and group it according to the discrete states that are discovered, okay? And then show the, basically when the square pops on is the start, so these are a bunch of different sort of mouse sequences, and when the square comes on, they're all starting one of the syllables, one of the sort of shared syllables. So they're all kind of doing the same thing while the square is on. And this is a rear, so this is where it's like coming up on its hind legs. So you can kind of see that because it looks, this is a top-down depth view, so it's kind of getting scrunchy and then coming up. This is the same thing, but it's coming down. And this is grooming, which really just means it's like messing with his tummy. And so I'm not going to spend a lot of time sort of talking about the neuroscience of this. What I want to end on is kind of it's kind of like one way to view what we're trying to do overall here, which is the way we understand a lot of supervised learning is that we're trying to learn a basis in which a linear classifier does a really good job. whether you're talking about a kernel machine, or whether you're talking about boosting, or you're talking about a deep neural network, at the end of your neural network, you're going to have like a logistic regressor, right? And so a lot of the work, maybe all of the work that we do these days is about trying to find awesome bases, whether it's through backpropagation, convolutional neural networks, or whatever it is. We want to find a way to warp a nonlinear space such that a linear classifier will do a good job. So what this agenda broadly here is to do the same thing with probabilistic unsupervised learning. Find warpings such that a Gaussian mixture model works, or a linear dynamical system works, or whatever your favorite kind of simplistic thing that's equivalent to a logistic regressor or a linear SVM. How do we find the warping? How do we find the kind of the basis such that those kinds of simple things can work? So to wrap up, the point is that we can build better probabilistic models with big function approximation. So neural networks are good at the high dimensional data. They're good at amortizing our variational inference. But we still want to take advantage of fancy message passing algorithms, conjugacy, and all that great stuff from probabilistic modeling when we can. And it turns out that we can view all of these through a single lens with automatic differentiation. And both a single sort of mathematical view and a single code view, like one kind of API for doing all this different kinds of thing. Thank you all for listening.
So we have lots of time for questions.
Yeah.
So you talk about deep nets being more aligned with like non-parametric stats than like classical parametric models because they're small. But has there been like further unification with like current non-parametric stats? Like how are you picking the capacity of either the deep net for inference or of your latent space? Like is there like racially processed latency?
Yeah, so here you mean, when you say modern non-parametric statistics, do you mean like combinatorial type stochastic processes like the Dirichlet process, or?
Yeah, like even in mixture models.
Yeah, so I don't have a good answer for that, because I think our understanding of deep density models is very weak. The thing that we understand really well are Gaussian processes and their relationships with neural networks. So you know, it's like 20-something years old now, but there's this really nice paper that shows that you can view a Gaussian process as an infinitely wide neural network, and it induces, it has a sort of standard like tanh neural network induces a particular kind of a covariance function for Gaussian processes. And this isn't necessarily useful in of itself, but it does give us a way to reason about, it gives us a nice mathematical model for neural networks, and a way to kind of talk about how that literally then, that neural network is then literally like a Bayesian non-parametric model. But as far as kind of connecting, but the density side of thing, I think it's much harder. So I don't honestly have a good answer for that. Regression is a lot easier. Yeah.
How hard do you think it would be to apply this kind of stuff to reinforcement learning as opposed to supervised learning?
So this is something so this is not supervised learning, by the way. This is all unsupervised. There's no labels. Okay. So when I say the mouse is grooming, I mean after the fact we segmented a bunch of data, and people who know a lot more about mouse behavior than me go in and say, oh look, the mouse is grooming coherently across all these syllables, and and so the point is to try to actually do that segmentation without a human providing the labels, because of this sort of argument that then the labels you get don't depend on a human having come up with them, right? The segmentation doesn't depend on the humans. Now, the caveat being that you have to think about time scale, and so there's the segmentation necessarily relies on a kind of a prior that you choose on how long the mouse is doing coherent things, and that is not something that's well defined, but it's something that you commit to as an assumption. And so then you get to be quite clear about it. But to answer your question about reinforcement learning, so I'm quite optimistic about this as a way to sort of like strike a balance between model and model-based and model-free. So model-free is a disaster, right? Like it doesn't actually work. And so everybody knows that model-based is the only way forward, but lots of times it's hard to come up with a model that makes sense, and that for all the same reasons that probabilistic graphical models are hard for real data, it's hard to connect a model to high-dimensional real data, Atari games, or whatever it is you care about. And so the question is like, how can we build models that can actually explain the world? And this is an attack on that you could kind of imagine. You could imagine sort of performing planning in a discrete latent space that's explaining the high dimensional observations. So we haven't done it, but I'm optimistic. Yeah.
Do you have any sense of how this type of approach might compare to, say, like learning a basis through self-supervised learning and then connecting that to probabilistic graphical models?
So self-supervised learning sort of can mean a lot of different things. So maybe you can be more precise about.
It's like the context of supervision type of thing.
Yeah. So you mean like predict the next frame of the video, or like?
Right. So using that to learn features rather than doing it kind of end-to-end in an unsupervised way with a graphical model.
Well, I guess I don't view something like modeling the next frame of video as being interestingly different than unsupervised learning, because you're still winding up with a joint distribution over the data, right? I mean, that's why I was saying self-supervised learning I think can mean, I mean, maybe I'm not up to date, but I view that as being like, can I come up with a clever way to get labels from my unlabeled data, right? And the natural thing you might think of here would be something like, would be like forward predictions or something. Although maybe we could come up with other things like, can you predict which mouse this came from, or something like that. These kinds of things like often work well. The challenge is, do you believe that whatever sort of statistical structure that you discover that way, is that going to be relevant to the science you want to do? And the answer is maybe, but I don't have a good answer for what the right kind of structure to look for would be, other than we think there are discrete behaviors, and so we kind of wrote down a big model. Yep.
So that's the first one is, do you see like an advantage of your model as being one that kind of avoids very general sampling-based inference? And second, it seems like the philosophical motivation is pretty similar to policy programs. So do you think like the framework you presented is kind of like a better alternative, or I don't know if you have like.
Okay, so sorry, repeat the first question again.
Do you see it as an advantage that you're not actually really like relying on like very general like MCMC-based inference in your model, and that you're kind of like trying to exploit like consciously where you see it and use neural nets for like, other things? Or do you see that?
Yeah. So I would say that like I love MCMC, but I try to be practical. And here we want to do things at scale, and it would be tough, I think, to get MCMC to kind of do the right thing at scale here, even in the absence of a neural network. And doing MCMC for the latent stuff sort of with a neural network attached, I think would be even harder. What I like about variational inference in this case is that I've got one optimization problem, and I can view my inference as an optimization, and I can view my neural network learning as an optimization coupled to that. So I have kind of, like one objective, whereas I think it would be kind of tough to come up with a Markov chain Monte Carlo algorithm that didn't wind up sampling from the neural network posterior in some way, and like there be dragons. Like that's not going to work. You had a second question, probabilistic programming. So I view probabilistic programming as like a really awesome abstraction and a really wonderful way to think about how to build very complicated probabilistic models, but it's not ready for prime time on the inference side. And so in general, if you're willing to, so here I'm writing down a particular model in the case of the mice, and a framework for importing existing graphical models for the more general case. I could replace that with a probabilistic program, and then hang neural network observations off of my probabilistic program. But almost none of the tricks I just described would work in that case. And so it would be at least as hard as probabilistic programming is now on the inference side, which is to say, so hard that it kind of doesn't work. Except now I also have to learn a neural network too. Yep.
So when you're actually doing science, one of the things you do is segment things at the observational level, but then you find patterns among the things you segmented at the observational level that give you, even more latent variables.
Yeah,
and sometimes what happens is those latent variables actually make you restructure the evidential variables, and that doesn't just happen in science, it happens in, say, cognitive development from one stage of understanding something to the next. So do you have any thoughts about how you would tackle that problem, or if that's
I think it is, because there are priors here, right? I mentioned length scale as a really salient one, but there are kind of like others too. Like for example, this is a Bayesian non-parametric hidden Markov model, and so that gives me a distribution over kind of how many states I expect to have represented in a particular finite data set. And from a scientific point of view, there's a big difference between saying this mouse exhibited 30 behaviors versus this mouse exhibited 10,000 behaviors. And so in kind of closing that loop, I think that's exactly the kind of those are exactly the kinds of things that we wind up sort of iterating on, if that answers your question.
So you think it's like having simplicity constraints? Is that?
Yeah, they are simplicity constraints, because in general, if you sort of allow for the possibility that, I mean, the data, given the opportunity, would say that every single frame is unique, right? And so we're necessarily sort of constraining, or adding bias to compensate for that variance, but there's no ground truth. There's no one true mouse behavior, and so we have to sort of agree that we're going to coalesce some set of them together and live with that bias in order to be able to summarize the mouse and to, like, say how much time it's spending at one state, or summarize like the effect. Like, for example, one thing you get is like a Markov matrix over the dynamics of the mouse. So, you know, it does this and then it does this, like 80% of the time. And then if you use like optogenetics and stimulate its brain with a laser, then it really hits that, like that transition matrix, the kind of like higher order effects. But there's no sort of like ground truth that we're trying to estimate. It's like a microscope. We have to set the focus on the microscope to decide what size of things we're going to look at.
Is there a natural way of integrating this with experimental design too, which would be a typical way?
Yes. So we have like thought a lot about that, but it's like, for example, I mean, sounds like total insanity, but you could imagine having the mouse on a screen, for example, and we like naturalistic behaviors, but we're really interested in interactions and social behaviors and things like that. And you could imagine trying to look at, infer the current state of the mouse and then present it with different stimuli in response to that. But it just amplifies the complexity of all these questions. Yep.
Me?
Yeah.
So I was really curious, when you're talking about, I guess, this sort of link between proximal stuff and natural gradient. So there's been a lot of recent work on reinforcement learning. Go back to a previous question about like training reinforcement learning, like neural networks that passes reinforcement learning with a natural gradients, or better, like trust reason policy optimization, that kind of thing. Do you see a link between, I guess, what those things are trying to do, like come up with a more, I guess, like you were saying, more in the latent space optimization direction, and your sort of more structured approach of generating things that have an easy sort of natural gradient?
Well, I guess in general, I guess I sort of think of this as a question of like, what is the geometry that I want to induce on my space? And when that geometry is cheap and easy, then we'd like to use it. There has been this agenda, for example, of KFAC and things like that, to try to induce to find sort of good approximations to the Fisher gradients, even in the sort of like general neural network case. And one thing we haven't done, but I would be sort of optimistic about, is using KFAC for the place where I said, everywhere where I said, and here you're stuck with flat gradients for your neural networks. You might reasonably believe that you could find the right geometries for those. Does that answer your question?
I guess like, so you're sort of saying like, like maybe there is sort of already like efforts to, or I guess so. I guess another part of my question was, do you think that this, I guess, sort of like as a follow-up, do you think this idea of encoding more explicit natural gradient sort of things, like things that can produce more explicit natural gradients that are faster, can be applied? I guess then my follow-up question is that guy's question, like, can this be applied generally to like reinforcement learning or something?
Well, I mean, natural gradients in reinforcement learning, I mean, are an old idea, right? I mean, I think Sham Kakade wrote a paper on this in 2003 for natural policy gradient or something, right? I mean, so it's and Amari's book is from, I don't know, late 80s. So so I think it's really just a question of trying to be clever. I mean, like so many other things, right? There's like a cleverness of like, how do I choose my model in sort of a smart enough way that things are going to be easy later on, and that's kind of what's clever about SVI, is that when you have that structure, then you get natural gradients easily, and in MDPs sometimes you can get that, but I'm not sure that the sort of like exponential family conjugate structure tells us that much about the right way to do it for MDPs. I mean, maybe it does. I don't know. You could imagine saying, I'm going to use these kinds of models for learning my model in model-based Bayesian RL, and then maybe you could do then natural gradient in the variational updates for that model learning, but that's pretty speculative.
Okay.
Yep.
Two questions. So firstly, what kind of domains do you think something like SVI can have like an immediate impact on that we haven't been able to do before? And secondly, what about neural networks as opposed to say a non-deep model from the like 2000 models, let's say like random forest, something like that? What about a neural network makes this SVI possible? So what is it that why is this that this idea didn't work before if I just chose like a random forest to plug in for my recognition, for instance?
Okay, so the second thing, so basically this would work for if you have a family of function approximators you want to use and you can get gradients through them, then this whole trick would work. Like, I don't think there's any real barrier to, I don't know, use gradient boosting or something with this. I think it boils down to this kind of like prior question. You know, early on I said the reason this is all working is because of convolution. And so I think part of the reason all of this has been successful is because it would be quite hard to replace something that currently works with a COMNET with like a decision tree. That said, like computer vision, like was a successful field before deep nets came along too, right? So I think like you could reopen that book and probably have a lot of the same successes. I think the SVI aspect of it in some ways, I mean, advances in stochastic variational inference and automatic differentiation within machine learning, I think are the two ingredients actually. What was the first question?
Sort of what domains do you think SVI is going to have immediate impact on?
Oh, well, I mean, stochastic optimization for problems we were otherwise doing, we were not doing stochastic optimization is often kind of a generic win. I mean, we use like stochastic optimization for Bayesian inference in a lot of different ways. I mean, tech companies are using it in ad systems, like Dave Bly and his group use this for all kinds of different scale. I have a paper like doing large scale astronomy, for example, in the Sloan Digital Sky Survey with folks up at Berkeley National Labs, where we're doing SVI to try to infer, basically a catalog of every light source in the in the universe, for example. So I think it's definitely having impact. Yep.
In the first paper about decomposing the graphical model for neural net, and that work has focused on reducing the hybrid models and the methods that are traditionally learned faster and with the traditional generalized better than the traditional models. Are there any other methods or models are available for integrating in future that we don't need removing explicitly labeled data or like training sample efficiency?
There's no label data in any of this. We haven't used any label data in any of this. Has all been unsupervised. Okay, so the labels, when I show you a picture of the mouse grooming itself, that's like somebody coming along later and saying, what is this cluster, right? This is all unsupervised learning. But in terms of sample efficiency, I mean, I think that is a question. I think probabilistic graphical models, part of the thing that makes them interesting is their compactness makes them sample efficient. It's the neural network that's the hard part of that. And so I think as we get better at better sample efficiency in our neural networks and they start to work on smaller data regimes, then I would expect to get more mileage out of these kinds of models as well. Yeah?
Yeah, so I was wondering about your initial motivation. You were talking about how this could be really useful for science in general, because you get a lot more information out of the mice looking at them automatically than those other kind of experiments we were showing before. I was just wondering, has that started to permeate through, like, have people taken this up in their biological experiments?
Yeah, so there's two things. I mean, so one is the view that like let's do semi-parametric modeling with neural networks, and that might be useful for a lot of different kinds of science because there are parameters we want to investigate, but maybe that's hard to map to observations. And there are some specific cases like astronomy and things where I think we've had some success with that, but it's a big lift for somebody who's not a somebody who's not a machine learning expert to get a model like this going still. In the mouse sort of world specifically, there are a few sort of strains of mice that get studied all over the place. And so part of the objective, I didn't sort of talk about this, but part of the objective here is to tackle this reproducibility question and to make it so that you can buy a Connect, download the pre-trained model for the strains of mice that you already know how to deal with, you can then, in a, relatively inexpensively and rapidly, set up a way to segment your mouse's behavior that will give you the same answers that they got at Harvard, right? And that is something that does not exist in behavioral neuroscience, and at any kind of like interesting level of complexity. And so so that's part of the sort of setup, is actually that not that people who care about mice would rerun all of these experiments, but that they would take the weights and everything, and that like that grooming syllable, when you ran it, you would like get the same one. So it would kind of be all about inference for the users of it. And there's a startup actually that's commercializing this, and that and so to try to actually get it kind of out the door to lots of different research groups, both like in industry and in academia. Yep.
One thing I was wondering about is like how general is this technique? So, for instance, for your data, you cut out a window that contains the mouse. So, like in the original video, there's 2 factors of variation. One is like the position of the mouse, and one is what behavior it's doing at that position. So you're kind of like pre-processing the data to normalize away a factor of variation. So I'm curious how you think this approach would work. So one example would be just the raw video without extracting out the mouse's position, and then like something more general, like what if you had a data set of video of humans doing different actions and segmenting out. I'm just curious, like how much do you think this approach would scale, or like what were the decisions involved in trying to like simplify the problem?
So the structured variational autoencoder sort of framework is general, right? Like it doesn't depend in an interesting way on it being frames
right.
of.
I know it's general, but I'm just curious in terms of like how well do you think it would perform in like a more complex domain?
I mean, we've applied it to other things like NBA basketball and zebrafish and things like that. And but the pre-processing you're describing, I mean, it is mostly a pragmatic decision, right? Like when you have when you can do good pre-processing, your system will almost certainly sort of work better. But more generally, we want to be able to do things like social behavior and lots of other stuff that would have absolutely more complicated observations. A high-level takeaway, though, is that this is like a recipe, and not like, I'm not saying use a switching linear dynamical system with a neural network for everything, so much as kind of like a philosophy around building these kinds of models, where if you had like a view, okay, I think that I have this high-dimensional data, but I think it's actually an admixture with particular kinds of structure, and the challenge is how do I have that kind of model with high-dimensional data? This is a recipe for sort of getting efficient inference and balancing kind of the kind of nice conjugate structure against the high-dimensional observations. So I'm pretty optimistic about that general recipe. Yep.
This is similar to the previous question. I really like the framework and the concept. In terms of making it like really easy to deploy for new problems, it seems like you'd want a way to sort of anchor the interpretation that you want to sort of the learned hidden states.
Yeah.
Is there like a good way to incorporate that kind of thing?
I mean, semi-supervised learning is like a natural thing you might try to do, right? Where you say, okay, this is a frame of video that I am going to apply a label to. I've been saying no labels, but maybe you're willing to be a little bit anthropocentric because you know you're going to be later when you look at things. And there is this whole field called ethology, right? That studies behavior and tries to come up with coherent ways to do that. And you could imagine applying a little bit of sort of like classical ethology, and then to clamp labels for a few frames, and then sort of applying unsupervised learning to everything else that tries to be consistent with the kind of the like behavioral analysis framework you were bringing to bear on the problem. Yep.
So SPI can't handle streaming data because you have to recompute the variational objective all the time, and that's really inefficient. So my question is, how do you handle streaming data?
So streaming data is a really interesting thing because it doesn't make sense, right? Like, so streaming data in a Bayesian context is weird, right? Because basically, over time, your posterior should contract to a point mass, right? So the idea of Bayesian streaming, to me, is ill-specified unless you're willing to commit to some drift of the underlying global parameters, right? So that is to say that if you're willing to say something like, well, I have data coming in and it's not all from the same model, that every 2 weeks with some probability I get the model completely changes, or there's an AR process sitting beneath things that's causing my parameters to drift slowly, or some kind of notion of sort of accumulating uncertainty. Because if you don't have that, then I'm not convinced being Bayesian is interesting for streaming problems. Because just at some point, you've had enough data, your posterior is concentrated to a little spike, and there's sort of like nothing more to know. So you have to sort of have this other component. And so then I think what happens is you'll have now local global parameters, where some of the global parameters I was kind of writing with theta would now be like daily, or or would themselves kind of be local, would be temporally local, and you need to sort of perform inference over those in a different way than the sort of the static SVI setup. Yep.
Going back to the reproducibility point, like how would you do model checking in a hybrid like network inference and an actual mixture model setup? Because like they might have just done their experimental setup incorrectly, or like it's eliminated wrong.
Well, the experimental setup is kind of like a different challenge, I would say. Sure. But there's no reason that these kinds of things don't lend themselves to like posterior predictive checks and things like that that are relatively off the shelf. In particular, any kind of like model checking in which you're generating data, like you can do just fine. I mean, not all things depend on that, but that's a big chunk of Bayesian posterior predictive checks kind of look like that.
So to refine the question about action, like, do you think there is value in the form of framework you've made in helping people reproduce the setup?
Oh yeah, yeah, sure, yeah.
So could you do like a gradient saliency to like try and actually get your experimental setup correct? So like, I'm not at Harvard, but I'm down the street. I want to do the same math experiment.
Yeah, well, I mean that's part of the story. I mean that's something that we've released the code. Like we want people to do that, and we want to feel good about it. That it's annoying for the same reason that if you train a neural network and I train a neural network, we may wind up with very different neural networks. But but yeah, absolutely. I mean, there's like sort of meta reproducibility and sort of low level reproducibility. We're assuming neuroscientists in general aren't going to like retrain the model, but like some people hopefully will.
Any more questions?
Yep.
Is there someone from HPN here? Okay. All right, why don't we thank our speaker again? If you're in the class,